In this video, we're going to be going through an overview of the basic refrigeration and charging procedures. These slides are out of Basic Refrigeration and Charging Procedures textbook available from HVAC Excellence. The slides are arranged in the same order as the 4 chapters in the textbook. It's actually a pretty decent textbook. It's optional for the classes that I teach, but it's a pretty decent textbook. It's a good reference guide. Again, that's available through HVAC Excellence. So let's talk about refrigerant pressure, states, and conditions. For some of you, this is going to be reviewed. Refrigerant is defined as the movement of heat from a place that is not wanted to a place that is unobjectable. In basics, this means we're going to take heat from a cooler, a house, or whatever, and we're going to put it into the outside environment where we really don't care that it's at. Okay, this picture shows a split system air conditioning system, but the same principles are in refrigeration. Okay, we have the load from in the house, the load out to ambient. That's refrigeration. We could have product load, okay, in a cooler. Okay, heat always flows naturally from hot to cold. With refrigeration, we're using compressors and temperatures and pressures to reverse that flow. So on the evaporator, okay, we have evaporating pressure, we have low side pressure, and we have suction pressure, and we have back pressure. Okay, all 4 of these terms are interchangeable to describe the low pressure side of the system. On the condenser, the high side, we have condensing pressure, we have head pressure, we have high side pressure, and we have discharge pressure. All 4 of those terms could be used to describe the pressures on the high side of the system. Now, it's very important to note when we look at these pressures, okay, that the 2 points of pressure change are the metering device and the compressor. Okay, so when we're talking low side of the system, you can take a line, an imaginary line, and you can draw it between the metering device and the compressor. Everything on the evaporator side, all those pressures should be the same. Everything on the condenser side, all these pressures should be the same. The condenser side is high pressure. The evaporator side is low pressure. No matter where you go in that system, the pressure should be relatively the same. The compressor is the heart of the system, okay, which circulates the refrigerant. It creates the pressure difference necessary between the low and high side of the system. The compressor raises the pressure and the temperature of the refrigerant vapor above the ambient and surrounding temperature. So when we raise that pressure and temperature of the refrigerant above the ambient temperature, which is your outside temperature, now the natural flow of heat moves from inside the refrigerant to outside, okay? Because heat will always move from high temperatures to lower temperatures. So what we're doing is we're raising that temperature, that refrigerant, over the temperature that is outside. Now, compressors are vapor pump only. Liquid refrigerant can damage or disable the compressor. You will never have, okay, liquid, or you should never have liquid in a compressor. So again, pumps vapor refrigerant only and divides the low and the high side. Then coming out of the compressor, we have a discharge line, okay? The discharge line is 100% high pressure vapor. Okay, connects the compressor to the condenser. The condenser, okay, rejects heat from the refrigerant because the temperature and pressures are higher than the temperature of the surrounding air, the outside air. The heat will come out of the refrigerant and be rejected to the outside environment. Out of the condenser, we have the liquid line. Okay, the liquid line supplies liquid refrigerant from the condenser to the metering device. Okay, and it should be liquid. Okay, if we're sending anything other than liquid refrigerant to that metering device, we may have a problem someplace in the system. The metering device controls the flow of refrigerant. It divides the low and the high sides of a system. So again, this is my second point of pressure change. My first point of pressure change is the compressor. My second point of pressure change is the metering device. Think of the metering device as you're putting your finger over the end of a garden hose. Everything on the garden hose side is liquid. Everything coming out from the metering device is a low pressure spray. Okay, in the trade this is known as flash gas. So liquid comes into the liquid line. There's something in here, it's a little pinhole that sometimes varies in diameter, and it sprays a low pressure sort of mist of refrigerant into the evaporator. That's called flash gas. The evaporator absorbs the heat into the refrigerant. Again, as this low pressure liquid comes into the evaporator, it starts to boil off. Okay, it evaporates because the temperature of that is now lower than the surrounding air. So we absorb heat into that because of that low temperature. As it absorbs heat, it boils off and becomes a vapor. Anytime we boil a substance or a liquid off, it takes a lot of BTUs. It absorbs heat as it boils off, and it leaves the area behind it feeling cooler at a lower sensible temperature. Removes the moisture from the air as well. Okay, because the evaporator is at a colder temperature than the surrounding air, okay, it does attract moisture. And that is one of the primary principles of air conditioning. It attracts moisture. The suction line connects the evaporator to the compressor. Okay, it sucks the vapor out of the evaporator into the compressor, where the cycle starts all over again. The suction line must be a low pressure, superheated, and we'll talk more about that in the future, vapor from the evaporator. Okay, there may be other components in the suction line, such as accumulators, crankcase pressure regulator, P-traps, or filters. But the suction line, these are the basic components of the refrigeration system. Every refrigeration system will have the four basic components: the compressor, the condenser, and the evaporator, and the metering device. The suction line, as I said, returns superheated vapor from the evaporator to the compressor. Occasionally, you'll have a receiver. Depending on the system design and operating conditions, a system may use a liquid receiver. A receiver is an accessory which stores refrigerant until it's needed for different loads placed on the system. That's sort of like a holding tank in the liquid line. Once the subcooled liquid exits the condenser, the receiver stores the liquid. The liquid level in the receiver will vary depending on whether the metering device is throttling open or closed. Receivers are used on systems which have modulating types of metering devices, such as thermostatic expansion valves. Some systems with a receiver may also have a receiver bypass to route the refrigerant directly to the liquid line to maintain head pressure. So the receiver is an accessory that's added to the liquid line to store liquid refrigerant. The condenser. Okay, we're going to talk about temperatures, pressures, and states. The condenser is under high pressure. How high the pressure and temperature of refrigerant will be is determined by the type of refrigerant, condenser efficiency, and design. The saturation temperature is the only point in the condenser where there's a direct pressure-temperature relationship, which can be plotted on a temperature-pressure chart. On an air-cooled condenser, the saturation temperature is normally 10 to 30 degrees above the ambient temperature. And on refrigeration systems with smaller condensers, you will see 35 degrees above the ambient temperature being normal. Okay, it comes into the condenser. Refrigerant comes in as a high pressure, high temperature, superheated vapor, which means the temperature of it is way above the condensing point. As it flows through the condenser, it starts to cool. It rejects heat. It will reach a saturation point where the vapor is changing to a liquid as heat is further removed. It's condensing. Once the refrigerant leaves the condenser at the condenser outlet, it's near ambient temperature, it's high pressure, subcooled liquid. In other words, the temperature is dropped below the saturation point. The evaporator also has temperatures, pressures, and states that we need to talk about. The evaporator is under low pressure. Again, how low the pressure and temperature refrigerant will be is determined by the application and the design. The saturation temperature is the only point in the evaporator where there's a direct temperature-pressure relationship, which can be plotted on a pressure-temperature chart. A low pressure, low temperature, about 80% liquid, 20% vapor, we call it flash gas, comes out of the metering device into the evaporator inlet. About halfway through the evaporator, and sometimes a little bit more, we have saturated vapor, the temperature in which liquid charge is changing to a vapor. In other words, it's boiling off. When we get to the evaporator outlet, we have a low pressure, low temperature, superheated vapor. And again, by superheated, we mean that between the point of saturation and the point of discharge from the evaporator, we are still adding heat. We're still absorbing heat into the system. So if my saturation point is 34 degrees, I could have 42 degrees at my evaporator outlet, okay, because I want to have between an 8 and 12 degrees superheat. So again, the superheat is just the difference between my evaporator outlet temperature and the temperature of my saturation point. Again, we're going to talk more about that, but it's sort of important. Okay, now let's talk quickly about subcooling and superheat. Okay, subcooling and superheat, we're going to talk the amount of liquid subcooling affects system capacity as well as the effectiveness and capacity of the expansion type metering devices. Expansion type metering devices basically is TXV, AEV. Subcooling is defined as the difference between the measured liquid temperature and the liquid saturation temperature at a given pressure. Liquid subcooling occurs from the start of the 100% saturated liquid point in a condenser and may continue all the way to the metering device. Saturated liquid temperature can be obtained from a pressure-temperature relation chart using condenser pressure. Okay, the concepts of subcooling and superheat are the two most important principles that the service technician has to understand before attempting to troubleshoot an HVAC system. Okay, so let's talk about this. Okay, we're going to talk about condenser subcooling. Condenser subcooling is the additional cooling of liquid in the condenser below the saturation point. It is measured by subtracting the actual condenser liquid out temperature from the saturation temperature measured in the condenser. In other words, your gauge pressure converted to temperature. If the pressure drops in the system, the pressure must be measured where the temperature was taken. Subcooling is needed to prevent liquid line flash. In other words, we do not want bubbles or vapor in the liquid line. Condenser subcooling ensures that there's a liquid seal at the bottom so the liquid line or receiver is never fed with vapor. Okay, so we have, okay, this is an R22 system. Okay, we have a little bit over 200 psi, which converts, we'll talk about the conversion here in the next slide. So we're taking our pressure of the high side, we're taking our temperature on the liquid line as it comes out of the condenser. Okay, that's condenser subcooling. Okay, 210 psi equals 105 degrees is our saturation point. Our liquid line, we're measuring right at 100 degrees. So our subcooling is 5 degrees Fahrenheit. Is that right or wrong? We really don't know on newer systems. We have to look at the manufacturer specification. Okay? So total subcooling, we go over closer to the metering device. We have 210 psi. That doesn't change. Okay, my pressures don't change throughout the entire high side. But my temperature may actually change the further down the metering device I go. Okay, so in this case, 200 psi, 105 degrees. My liquid line is 95 degrees. So I now have a 10 degree subcooling. Superheat is any heat added to a completely saturated vapor that results in a rise in temperature, sensible heat change of the gas. Superheat tells me what's happening in the evaporator. So once again, I'm going to use my pressure gauge. In this case, I'm going to use a low side pressure gauge because, again, I want the pressure of the saturation point, which is happening in my evaporator. The low side pressure gauge, no matter where it's connected on the low side of the system, tells me what is happening in the evaporator. The pressure tells me the actual temperature of the evaporator, of the saturation. Okay, so we're talking evaporator superheat. You take your temperature closest you can to the sensing bulb or the outlet of the evaporator. So if my gauge is showing me 76 psi, that converts to a 45 degree saturation point. If my temperature is 60 degrees, I take 60 minus 45, and I now have a 15 degree evaporator superheat. That's a little higher than I'd like it to be. I'd like it to be between 8 and 12. Total superheat can be taken at where the suction line is closest to the compressor. This is what we normally use when we deal with system service. Okay, total superheat. So again, my suction line temperature, 60 degrees. My system pressure is 76 on the low side, which equals 45 degree Fahrenheit. So my superheat is 15 degrees. Again, that's a little bit higher than I'd like it to be. There's different types of metering devices. We have capillary tubes, we have automatic expansion valves, which is AEVs, we have fixed bore, and we have thermostatic expansion valves. As systems become more and more efficient, we're seeing more and more of a change to the thermostatic expansion valves. Small systems like window air conditioning systems will have the cap tubes. AEVs are used in some refrigeration systems, and fixed bore is used pretty often in residential and light commercial air conditioning and heat pumps. So cap tubes are low-cost devices, have no moving parts, and can be used on a wide range of applications. Thermostatic expansion valves are the most efficient. They maintain a constant evaporator superheat, and they help prevent compressor flooding. TXV types could be pressure limiting, balance port, so they're externally equalized, and we'll talk more about that. They could be internally equalized, and they could be electric operated. Electric operated are by far the most efficient, but since you pay for what you get, they're by far the most expensive. TXVs have bulbs, okay? They have a bulb that has to be placed on the suction line. You cannot place it any place from the 3 o'clock through the 9 o'clock position. They cannot be on the bottom of a suction line because the bottom of the suction line contains oil. Okay, vertical installation, the pilot tube must be up, but it's not recommended. You cannot place it on a vertical pipe with the tube coming out of the sensing bulb down. The actual charge will drop from inside the bulb. Okay, you want your TXV equalizer to be as close to the evaporator outlet as possible, but it must be on the evaporator side of a balancing port. In a lot of larger evaporators, multi-pass evaporators, we have an extra line that connects into the suction line. That's called a balancing port. Automatic expansion valves maintain a constant evaporator pressure. They're used in small systems which have constant loads. Fixed bore metering devices are the most common on the residential systems. They are a dual purpose device. It works as a metering device and it works as a check valve. They're considered critical charge. In other words, we weigh that charge into those systems. So, how do we know if a refrigerant charge is correct? Okay, all refrigeration systems differ in the amount of charge they hold. There's different amounts of line set, there's different purposes, and there's different conditions they operate in. There are guidelines and charts and techniques to follow for charging and verifying charge. System design and layout must be known. How long and what size of line set? What's the volume of the filter dryer? All of these things can actually mess up a charge. If you change a filter dryer with a larger size filter dryer, which happens occasionally, your required charge may change because the volume of that filter dryer may change. So if the system has a TXV, you have to charge the system under a high load. In other words, charge it for the conditions the extreme conditions it's meant to charge for. Charge as a liquid when possible. Throttle liquid blends into the low side. If it's a blend, do not charge it as a vapor because you do not know the components of the refrigerants that are going to go in there. Record evaporator and compressor superheat and condenser subcooling. Cap tube or fixed orifice air conditioning systems. Weigh in the correct charge. Use the manufacturer's charging charts. There will be charts on the equipment. On air conditioning and heat pumps, this is usually right inside the wiring cover. You might have to go to a manufacturer website, but you have to weigh in the correct charge. You always want to use system superheat method to verify the charge. Okay, so for TXVs and AEVs, okay, we're using basically subcooling. Okay, superheat should be constant. Okay, you want to record it just to verify. But for cap tubes and fixed bore, we are always using superheat method. Okay, system superheat. Okay, requirements for system superheat charging: proper evaporator airflow, accurate remote bulb tester, accurate gauge manifold set. So if you basically what we use the indoor wet bulb temperature, okay, this temperature, wet bulb temperature around the evaporator, and we use the condenser entering air temperature, and then we use a chart that tells us what the superheat should be. So for example, okay, if I have an indoor wet bulb temperature of 64 degrees, an condenser ambient temperature of, let's say, 80 degrees, I should have a superheat of 15 degrees. To increase superheat, remove a refrigerant. To decrease superheat, add refrigerant. So here's an example. Okay, suction line temperature 60 degrees, 76 psi is 45 degrees Fahrenheit. My superheat is 15 degrees. Okay. Is that higher than I want it to be? Yes. I want 8 to 12. So in this case, I would add some refrigerant to lower that superheat, increase the refrigerant in the evaporator. Okay, airflow can be measured in many ways: equipment data charts, airflow meters, or a combination of meter readings and formulas. There's a thing called a sensible heat formula that you'll have to use all the way through this trade. So CFM is cubic feet per minute. It's a measurement of airflow. So if we take our sensible heat BTUs, divide it by 1.8 times the temperature difference, we can calculate how much airflow. So BTUs equals heater amps times volt times 3.41. This is for electric heat. Okay, three-phase would be heater amps times volts times 3.41 times 1.73. That tells us sensible heat BTUs for an electric heat. For fossil fuel, it's a little bit different. Again, BTUs is heater input times efficiency or bonnet capacity. This is really not required for refrigeration, but again, this formula you really do need to know if you're going into this trade. Okay, when you measure airflow, you measure with a tool and you take multiple readings all the way through and then you average it out. Okay, some sample questions you might come across on some testing or certification testing. The high and low pressure points in a refrigeration system are separated by what? The correct answer is A and C. The compressor and the metering device are my points of pressure change. Subcooling can be defined as you have four choices: the cooling effect of an evaporator, any sensible heat removed from 100% saturated liquid, the superheated that is removed at the top of the condenser, the cooling of the compressor motor by returning refrigerants. The correct answer is B, any sensible heat removed from 100% saturated liquid. Always charge a TXV with a receiver and a sight glass under, okay, so we're talking about charging with a TXV system. We want to charge with no load condition, low load condition, high load condition, or none of the above. The correct answer is C. Okay, high load condition. By the way, we're not going to charge using the sight glass. You're going to charge using subcooling. Superheat is defined as the heat added to the saturated liquid, heat removed from the saturated liquid in the condenser, heat added to the saturated vapor exiting the evaporator, or heat removed from the saturated vapor exiting the evaporator. The correct answer is C, the heat added to the saturated vapor exiting the evaporator. Okay, and one thing again, this is back here, this is a trick question. Okay, here's the key is TXV. Okay, ignore the sight glass because you are never going to charge using a sight glass. Okay, so if you believe that this question says charge a TXV with a receiver and sight glass, okay, you're not charging ever using a sight glass. You might charge a system that includes a receiver and a sight glass, so just be careful on that question. Okay, so this is a sort of a long drawn out example of the components, the charging requirements, and how to troubleshoot the refrigeration side of a system. Okay, we're going to talk much more about the troubleshooting, but it's an important basic procedures.